Hello everyone, my name is Jan. I'm a PhD student at Columbia University. If you were here for the keynote, you might remember Henning mentioning lots of difficulties in developing distributed and heterogeneous IoT applications. During this talk, I'd like to show you a little bit more practical side of that. I'll try to do two demos, one recorded in a video and one live, so we'll see how that goes. The topic of this talk is about building distributed IoT applications that use or contain audio-video processing blocks. We have an ongoing research project called SECE. SECE stands for Sense Everything, Control Everything. And in the previous talks about fog computing, you might have seen the benefits of distributing IoT applications closer to devices. But the problem is, and the bigger research problem is, we don't really know what those applications would look like or what the right abstractions for building such distributing applications are like. It turns out that designing applications for heterogeneous systems and especially applications that run on a network of devices is a pretty hard problem, although there are many benefits. Security, privacy, scalability, and resiliency are some of those. The problems that we are most concerned with are privacy-oriented problems. As if you're familiar with what's available in terms of existing IoT frameworks, you probably know that most existing frameworks let you deploy some form of IoT application to the cloud, where all the data processing takes place, and individual IoT devices simply transfer all the data to the cloud. That may or may not be fine. It's probably fine for simple applications or for simple devices, but as soon as you introduce something that is privacy sensitive, let's say a video camera in your living room, then you really have to worry about whether or not the cloud infrastructure your application running on is trustworthy. So this is what the architecture of the SECE system looks like. So we have been sort of trying to design something called a personal smart object cloud, which is essentially a network of IoT devices, and then for each type of device, make it possible to deploy a subset of application functionality directly onto the device. So for example, if you had a Raspberry Pi as an IoT device in your network, it would be possible to deploy some application module onto the device. You could deploy some application component onto devices running the web browser using JavaScript and so on. So this is very, very similar to the fog computing concept, except that we have been sort of trying to push the application deployment all the way to the end device itself. For many of the devices that we use today, that is possible. If you use a Raspberry Pi or a BeagleBone Black, you could run entire Linux containers on that. So there are already existing mechanisms for pushing applications to such devices. For some of the smaller devices, like Arduino, Teensy, you could not typically deploy an entire application over the network, but you could push a subset of it, for example, in form of programmatic filters or tiny little scripts. Very often you need this kind of functionality for real-time control loops, where you would have a device A and a device B that are somehow communicating to control a physical process. In this case, very often latency is what matters, so we need to find a way to program one device to send sender state updates to another device, which will use the data to control some kind of actuator. And then for on-device processing, imagine a very simple application where you would like to design an IoT-like home security system or a baby monitor, for example. So you buy a video camera that is connected to the internet, and the camera, the video stream from the camera is fed into some kind of vision processing block which tries to detect motion or do facial recognition or do similar things. The way people achieve that today is that they would stream a raw video stream from the camera onto some cloud infrastructure, which will then run OpenCV-based processing algorithms. Such products are on the market today, and people do that. Whether or not this is secure depends on whether or not you trust the infrastructure. But if you already have an IP-connected camera, chances are that there is a full Linux computer inside, and there is absolutely no reason why it should not be possible to perform some video pre-processing directly onto the device to remove some sensitive information from the video stream before sending it off to the cloud. I'd like to show you a demo of that. So on Columbia campus, we have 3 elevators in our building that very often go out of order. People get stuck sometimes in those elevators, and it usually takes like an hour or even more for somebody to come rescue them. So we have been thinking about trying to put together a retrofitted monitoring system based on a video camera connected to a Raspberry Pi, which we will simply install in front of the elevator control panel, and then we'll try to do vision-based analysis of the control panel to see if we can detect whether or not those elevators are stuck. This is roughly what the system architecture looks like. On the left, you see a camera connected to a Raspberry Pi, and the camera is capable of doing real-time streaming. So you can get a real video stream from the camera over the network, but that video stream is only accessible from privileged applications. For example, the control panel on the right would be a privileged application if you wanted to see the real-time video stream. In addition to the streaming program, the Raspberry Pi is also running a small application that does feature removal. Imagine this as some processing block that removes some privacy, some insensitive information from the video stream. For example, if somebody walks in front of the camera, it should not be possible to recognize their face. Here is an example that shows what this kind of video processing would do to a credit card image. On the left, you see an image of a credit card. On the right, you see just the shape of the credit card. So this is the sort of processing that the Raspberry Pi directly connected to the camera is capable of doing. And the result of that processing can be then sent off to a cloud server for additional OpenCV-based processing to decode the state of the elevators. And then based on some events or irregularities in the operation of those elevators, the system could send a notification, send a text message, call a phone number, anything that you can easily integrate on the web. So we have implemented an early prototype of this system that I'm now trying to show you. So what you can see here is a very crude web interface. Since we don't have the camera installed in front of the elevator right now, there is a pre-recorded video that gets streamed in the loop. So this window in here shows a pre-recorded video of the elevator control panel. There are 3 windows on the control panel, each represents 1 elevator. There are 3 elevators in the building. And this video stream is being sent to cloud-based infrastructure, which is currently running on an Amazon cloud, which runs an OpenCV machine learning algorithm that extracts the state of individual elevators from the video stream. The boxes right here represent the information extracted from the video. So you can see the floor number of each elevator, and you can see whether or not these elevators are moving up and down. I'm not sure if you can see that, but hopefully the state of these elevators in here is extracted from this in real time. The image or the video stream that the algorithm that computes this work with is a binary image. It doesn't look like this. It does not process the raw stream, but we convert it to a 1-bit binary image to make sure that if anybody walks in front of the camera, you cannot tell who they are. And the idea here is that the video camera will be put in front of the elevator in the building in case there are further issues, so that we can show to the facilities people that we can actually do a better job at monitoring the elevator than they can do. And there is much more you can do. I mean, if you look at GitHub or any of the publicly available source code repositories, you'd find a lot of software for audio-video processing. You will find QR code detection, license plate detection programs, and facial and speech recognition applications. All those are within reach and easily accessible, so pretty much anybody who has rudimentary coding skills could download them and deploy them in form of containers or some kind of packages to the devices. So this is another application example which does QR code detection in real time. So you'd see the still frame was a video, and whenever you place a QR code in front of it, it's going to retrieve the URL from the QR code. At the same time, another video processing application was doing motion detection over the same video. The result of the motion detection application is this LED bar up here. So the more motion there is in the picture, the more LEDs are going to be turned on. So this is an example of application that is already distributed across a network of devices. Some simpler component of that application runs on the device itself, which in this case is typically the video camera device. The more CPU-intensive parts of the application are running on cloud infrastructure. And the user interface, which you can use to interact with the application, is a JavaScript browser application. Now, in addition to this kind of real-time processing, Columbia has a long history of doing practical projects and involving students. So we also try to use the same framework to implement a robotic license plate reader, which is connected to a text-to-speech system. So one of our visiting students from Germany did that over the summer, on top of this framework. So I'm gonna play his video to show you what can be done with audio-video processing and IoT devices.
Hey, my name's Tim, and we're at the Internet Real-Time Lab at Columbia University. I'm going to show you a robot project that we have built. So you see a model parking garage here, which is taped on the floor in the light tape, and then you can see some license plates over here, which are cars that are parked over here. And we have a robot, which is currently parked in its docking station, that we want to send to those license plates and make it read out the license plates. So we also have a user interface to control the robot, which you can see over here on my computer screen. We have a manual joystick to control the robot manually, and then we have a text-to-speech engine, which is currently running on the laptop over here. All the devices are connected via servers that are running in the cloud, and it's all connected on Wi-Fi on the internet. So let's see if it works. We first have to initialize the robot at its docking station, and then we see the floor plan over here, and then we can click the position where the robot is supposed to go. And when we make it move, the robot actually starts moving. So what it does now, it uses a so-called A-star algorithm, which means that it splits the whole floor plan into squares of 5 centimeters and then connects those squares in an ideal path. The whole path is computed in the cloud and then transferred to the robot, so that the robot is now navigating completely autonomously. And even if it would lose connection to to the server, it would still be able to navigate. Now that it has reached its destination in front of the license plate, we can make it capture the license plate. The picture is uploaded to the cloud.
New license plate detected. Sierra Golf 0 1 2 3 Hotel.
And the cloud server sends the result to the text-to-speech computer, and that one then reads out the license plate.
All right, I'll pause it right here. So this is an example of a heterogeneous IoT system. We essentially retrofitted a Roomba with a Raspberry Pi device connected to Wi-Fi and a camera. And when Tim started the application, it downloaded a very simple JavaScript application to the Roomba. What you cannot see in the video is that once the Roomba starts moving, the network can get disconnected and it's still going to work. As soon as the Roomba arrives in front of the license plate, it starts streaming video from the camera to the cloud, which then does the license plate recognition. All this is implemented using pretty much standard technologies. The application is JavaScript. We use WebRTC and WebRTC data channels for real-time communication. Since we already have this sort of infrastructure, there is also the possibility to use this to control the Roomba in real time using the joystick, which I will show you right now.
We also have a manual control. So when we toggle it to manual mode, I can use this 3D joystick to manually control the robot. So let's drive to the other license plate. And then we can also try to recognize the US license plate over here.
New license plate detected. Foxtrot Bravo Radio 1 4 4 9er.
So this is a fun sort of hands-on summer project that one of our students did based on the SECE framework. The larger research theme of this is, once you have this kind of infrastructure in place, how do you actually develop applications, distributed IoT applications that can run reliably, can respond to changes in the infrastructure, react to network outages, and how do you make it easier for IoT application developers to move from a centralized cloud-based infrastructure to more distributed systems. And since we are probably running out of time, I'll wrap it up right here and take any questions you might have.
Thank you. So Ian, I saw that you guys code the binary numbers on the elevator. What kind of smart device was that? And I apologize if you repeat this because I was missing maybe your introduction.
The smart device is a Raspberry Pi with a camera, USB camera connected to it.
So it wasn't an AC drive or something, it was a Raspberry Pi, the
the
one that
whole
controls the
idea,
elevator up and down?
The whole idea that I probably forgot to mention is that we are sort of trying to figure out how to do applications like that using off-the-shelf components. So you typically throw together a bunch of Raspberry Pis, USB cameras, Wi-Fi cards, and try to mold this into a functioning system. So there is a Raspberry Pi in front of the elevator control panel, which has an ordinary USB camera and ordinary Wi-Fi card, which connects to campus network. And the actual video processing that does a very simple machine learning algorithm on top of the video stream is running in the cloud.
Thank you. So the whole point for this project was for you guys to offer a visual of how the elevator works, or what floor is the elevator at every time?
So we want to extract that information and make it sort of actionable. So once you have this extracted, you can turn it into virtual sender devices, which is what the user interface showed. once you have virtual sender devices, you can subscribe to them. You can react to changes in state and so on. So the ultimate application is automated notifications to facilities whenever one of the elevators stops moving. So if there is no motion for, let's say, 30 minutes, we want to be able to notify them automatically.
Thank you.
I think you talked about doing some computer vision locally in some cases, and then sending another stream remotely. How do you make the trade-off between, I guess, what you do locally versus doing it in the cloud? You could potentially, for some applications, probably just do everything locally, right? But how
yeah, that's a great question, and I don't have the answer for that. This is one of the research questions that we've been trying to answer. So you typically know what sort of algorithm you need to run to implement an application like that, but figuring out how to split the workload between the device and the cloud infrastructure is something that you need to have some experience for. So you as a developer need to know whether or not your algorithm is capable of running on a Raspberry Pi, or whether you need to run it on cloud infrastructure. Ultimately, we would like to be able to somehow figure it out automatically, at least to some extent, using some hints from the programmer, but we don't have an answer to that yet. So for now, you as an application developer have to explicitly divide the application in two modules, one for the Raspberry Pi and one for the cloud.
Thanks.
Thanks for